Something extraordinary is happening in the night sky right now, and it defies every basic expectation we have about how celestial objects behave. Comet 3I Atlas, a wandering ice giant roughly the size of Manhattan, is performing what astronomers are calling a paradox in motion. Over the past 6 days, this comet has lost approximately a third of its brightness, its magnitude climbing from 10.1 to 10.6, which, in astronomical terms, means it now shines at just 63% of its former luminosity. Here is the crucial detail. During that exact same period, the comet has raced 10 million kilometers closer to Earth, a distance equivalent to 25 times the span between our planet and the Moon. Think about that for a moment. An object hurtling toward us at tremendous speed, closing the gap by millions of kilometers, and yet it grows dimmer in our telescopes, rather than brighter. It is as if someone were walking toward you with a flashlight, and with every step closer, the beam grew fainter instead of more intense. This is not how the universe is supposed to work, at least not according to the straightforward physics of distance and observation. The discovery, reported by the Solar Astronomy Laboratory at the Institute of Space Research of the Russian Academy of Sciences, has sent ripples through the astronomical community. And if you want to stay updated as this situation develops in real time, because trust me, this story is far from over, make sure to subscribe and turn on notifications. We are watching a celestial mystery unfold, and the data coming in over the next few days could rewrite what we know about cometary behavior. To understand why this dimming is so confounding, we need to establish what comets are and how they typically behave. Comets are not stars. They do not generate their own light. Instead, they are massive conglomerations of ice, rock, dust, and organic compounds, remnants from the early solar system, frozen time capsules that have drifted through space for billions of years. When a comet approaches the sun, solar radiation heats its surface, causing the ice to sublimate, meaning it transitions directly from solid to gas without passing through a liquid phase. This sublimation releases jets of gas and dust that form the iconic coma, the fuzzy atmosphere surrounding the nucleus, and the brilliant tail that streams away from the sun, pushed by solar wind and radiation pressure. The closer a comet gets to a source of illumination, whether that is the sun or, to a much lesser extent, an observer on Earth equipped with powerful instruments, the brighter it should appear. This is basic observational astronomy, the same principle that makes Venus dazzling at certain points in its orbit or causes the Moon to appear larger and more luminous when it is at perigee, its closest approach to Earth. So when 3I Atlas began its approach toward our planet, every model, every expectation, every historical precedent suggested that its brightness should increase proportionally. Instead, we are witnessing the opposite, and that contradiction demands explanation. Let's look closer at the data. The magnitude scale, which might seem counterintuitive to those unfamiliar with astronomy, works inversely. Lower numbers indicate brighter objects, while higher numbers indicate dimmer ones. The faintest stars visible to the naked eye under perfect dark sky conditions hover around magnitude 6, while the brightest star in the night sky, Sirius, shines at magnitude negative 1.46. Comet 3I Atlas, with its current magnitude of 10.6, is well beyond naked eye visibility, requiring at least a modest telescope to observe. The shift from 10.1 to 10.6 might sound trivial, a difference of just half a magnitude, but In the logarithmic language of astronomy, this represents a dramatic decrease in luminosity. Each whole magnitude step corresponds to a brightness change of approximately 2.512 times, meaning this half-magnitude drop translates to the comet now emitting roughly 63% of the light it produced less than a week ago. To lose that much luminosity over such a short period, while simultaneously closing 10 million kilometers of space between itself and Earth's observation platforms, suggests that something fundamental is happening to the comet's structure, composition, or activity level. The most straightforward explanation, the one that immediately presents itself when you map the comet's trajectory, is that 3I Atlas is moving away from the Sun even as it approaches Earth. Picture the geometry. Earth and the comet are not on a collision course in a straight line from the Sun. Instead, their orbits are oriented such that the comet's path, while bringing it nearer to us, is simultaneously increasing its distance from the solar furnace that provides the energy for its activity. As the comet recedes from the Sun, it receives less intense solar radiation. The heating that drives sublimation weakens, the production of gas and dust declines, and the amount of sunlight available to be reflected diminishes. It is a bit like standing in a room with a single lamp. If you step closer to a mirror on the opposite wall, while simultaneously moving farther from the lamp, your reflection will indeed grow dimmer, even though the mirror itself is nearer. The light source, not the reflective surface, dictates the brightness. But here is where the story becomes more intricate, where the clean narrative of orbital mechanics begins to fracture into possibilities and uncertainties. Solar distance alone might account for a gradual, predictable dimming, but the rapidity and degree of 3I Atlas's luminosity drop suggest that additional factors are at play, factors rooted in the comet's internal dynamics and surface properties. This contradicts what we previously thought about how predictably comets respond to changes in solar heating. Experts are now pointing to three interrelated mechanisms that could be contributing to this anomalous behavior: fluctuations in albedo, internal structural changes within the nucleus, and instability in the rate and pattern of dust ejections. Each of these processes operates on timescales ranging from hours to days, and each can produce sudden, dramatic shifts in observed brightness that have nothing to do with the comet's distance from Earth or the Sun. Let me take you through each of these mechanisms in detail, because understanding them is key to grasping why 3I Atlas is behaving so unpredictably. Albedo, in the simplest terms, is the measure of how much light a surface reflects compared to how much it absorbs. Fresh snow with an albedo of 80 to 90% reflects almost all the sunlight that strikes it, which is why it appears blindingly white and can even cause snow blindness in extreme conditions. Asphalt, on the other hand, has an albedo of only 5 to 10%, absorbing most of the light and appearing dark. Cometary nuclei typically have extremely low albedos, often in the range of 2 to 10%, comparable to coal or charcoal. This is because their surfaces are coated with dark, refractory materials, organic compounds that have been altered by eons of exposure to cosmic radiation, creating a sooty, light-absorbing crust. However, a comet's albedo is not static. As solar heating intensifies, sublimation can strip away this dark crust, exposing fresher, more reflective ice beneath, which temporarily boosts the albedo and makes the comet appear brighter. Conversely, when sublimation slows or stops, dust and dark particles can settle back onto the surface, reducing albedo and causing the comet to dim. Think of it as a mirror covered in dust. Shake off the dust, and it gleams. Let more accumulate, and it grows dull. For 3I Atlas, the current dimming could indicate that its surface is undergoing a transformation. Perhaps a thickening of the dark mantle as sublimation rates decline with increasing solar distance, or possibly a redistribution of surface materials driven by the comet's rotation, which could be bringing darker, less reflective terrain into view as seen from Earth. These albedo fluctuations are not unusual in cometary science, but their timing and magnitude in this case are striking, and they hint at a surface that is highly heterogeneous, a patchwork of ice and dust responding dynamically to changes in temperature and solar input. Now, let's turn to what might be happening inside the nucleus itself, because the nucleus is where the real drama unfolds. The nucleus of a comet is its solid core, the original body that has existed since the solar system's formation some 4.6 billion years ago. For a comet like 3I Atlas, with a nucleus comparable in size to Manhattan, we are talking about a body several kilometers in diameter, a massive aggregation of water ice, frozen carbon dioxide, methane, ammonia, silicate dust, and complex organic molecules. This is not a uniform, homogeneous block. It is more like a dirty, porous sponge, riddled with voids, cracks, and layers of varying composition. When solar heat penetrates this structure, it does not do so evenly. Ice sublimates first in the warmest regions, creating pockets of gas that build pressure beneath the surface. When that pressure exceeds the strength of the overlying material, you get outbursts, sudden jets of gas and dust that explode from the nucleus like geysers on Earth. These jets can dramatically increase a comet's brightness, surrounding it with fresh material that scatters sunlight. But jets are temperamental. They can shut off as quickly as they start if the vent becomes clogged with dust, if the ice source is exhausted, or if the rotation of the nucleus turns the active region away from the sun. If 3I Atlas experienced a significant outburst in the days before the observed dimming, and that outburst has now subsided, we would expect to see exactly what we are seeing, a rapid drop in brightness as the temporary enhancement fades. There is also the possibility of fragmentation. Cometary nuclei are fragile, and the stresses induced by solar heating, outgassing, and rotation can cause them to crack or even break apart entirely. Comet Shoemaker-Levy 9 is the most famous example. It fragmented into more than 20 pieces before colliding with Jupiter in 1994, an event that provided unprecedented insights into cometary structure, but also demonstrated just how delicate these objects are. If 3I Atlas is beginning to fragment, even on a small scale, the redistribution of material could alter its overall reflectivity and activity, leading to the brightness drop. Chemical changes are another factor. The surface of a comet is constantly being altered by solar ultraviolet radiation, which breaks down complex molecules and can create a darkened, weathered layer. This process, sometimes called space weathering, is analogous to how a banana left in the sun will brown and darken. If the surface chemistry of 3I Atlas has shifted toward darker, less reflective compounds, that would contribute to the dimming we are observing. So, what does this actually mean when we talk about instability in dust ejections? Dust is the key to a comet's visibility. The solid nucleus, even one the size of Manhattan, is too small and too dark to be seen from Earth without the aid of very large telescopes. What makes comets visible, what gives them their characteristic glow and tails, is the cloud of dust particles ejected from the nucleus and suspended in the coma. These particles, ranging in size from microscopic grains to chunks several millimeters across, are extraordinarily effective at scattering sunlight. When ejection rates are high, the coma becomes dense and expansive, and the comet brightens. When ejection rates fall, the coma thins, and the comet dims. The rate of dust production depends on several factors: the intensity of solar heating, the availability of volatile ices near the surface, the porosity and structure of the nucleus, and the comet's rotational state. Comets rotate, often with complex tumbling motions, and this rotation means that different parts of the nucleus are exposed to the sun at different times. If the currently sun-lit hemisphere of 3I Atlas has fewer active regions, or if those regions have become dormant, dust production would drop even if the comet is still relatively close to the sun. The solar wind, that constant stream of charged particles flowing outward from the sun, also plays a role. Solar wind pressure shapes the tail and can influence how dust is distributed around the nucleus. Variations in solar wind intensity, which can change on timescales of hours to days in response to solar activity, could alter the appearance and brightness of the coma as seen from Earth. There is also the question of seasonal effects, though seasons for a comet are not like seasons on Earth. As a comet orbits the sun, different latitudes of its nucleus receive varying amounts of sunlight, much like how Earth's poles experience continuous daylight or darkness depending on the time of year. If 3I Atlas is entering a phase where its most active regions are rotating into shadow, we would expect a decline in dust production and, consequently, brightness. These processes are interconnected and can amplify each other, creating a feedback loop that makes cometary behavior notoriously difficult to predict. I want to pause here and ask you a question, because this is where the science gets truly fascinating and where we need your perspective. Given what we know about the mechanics of comets, the interplay of solar heating, surface properties, and internal structure, do you think the dimming of 3I Atlas is a temporary fluctuation, something that will reverse as the comet continues its journey? Or could this be a sign of deeper, more permanent changes, perhaps even the beginning of the comet's disintegration? Is this a comet that is simply adjusting to its changing environment, or are we witnessing the slow-motion death of a celestial wanderer? Drop your thoughts in the comments below, because this is the kind of mystery that benefits from diverse perspectives, and I genuinely want to know what you think is happening up there. Let's look closer at the data from a different angle, considering the implications of what we are observing. The fact that 3I Atlas is approaching Earth while dimming creates a unique observational opportunity. As the comet draws nearer, even though it is getting fainter, our instruments can resolve finer details of its structure. Telescopes equipped with high-resolution imaging and spectroscopy can analyze the composition of the coma, looking for specific molecular signatures that reveal what volatiles are sublimating and at what rates. Spectral lines from water, carbon monoxide, carbon dioxide, methane, and various organic compounds can be measured, providing a chemical fingerprint of the nucleus. Changes in these spectral signatures over time can tell us whether the dimming is due to a decline in overall activity or a shift in the types of materials being released. If, for example, water production remains steady, but carbon monoxide and carbon dioxide decline, that would suggest that the outer layers of the nucleus, where the more volatile ices reside, are being depleted, leaving behind a surface dominated by less active water ice and refractory dust. Photometric monitoring, the careful measurement of brightness changes over time, can reveal periodic variations linked to the comet's rotation. If the brightness oscillates with a regular period, that indicates that the nucleus has a non-uniform surface with bright and dark patches rotating in and out of view. Such data can help astronomers construct a rotation model and identify where the active regions are located. Radar observations, though challenging for an object at 3 atlases distance, could potentially provide direct measurements of the nucleus's size, shape, and surface roughness, offering constraints that photometry and spectroscopy alone cannot provide. The broader implications of 3I Atlas's behavior extend beyond this single comet. Every comet is a probe of the early solar system, a sample of the primordial material from which the planets formed. By studying how comets respond to solar heating, how their surfaces evolve, and how their internal structures hold up under stress, we gain insights into the conditions that prevailed in the outer regions of the protoplanetary disk more than 4.5 billion years ago. The volatility of cometary brightness, the sudden outbursts and equally sudden fade-outs, underscores how dynamic and unpredictable these objects are, and that unpredictability has consequences. If humanity ever hopes to visit a comet up close, as the Rosetta mission did with Comet 67P Churyumov-Gerasimenko, we need to understand these processes in detail. An outburst or a fragmentation event could pose serious hazards to a spacecraft in close proximity. More fundamentally, the study of comets like 3I Atlas informs our understanding of the inventory of volatiles in the solar system, the delivery of water and organic molecules to the early Earth, and the potential for similar processes on exoplanetary systems. Could the dimming of 3I Atlas be telling us something about the life cycle of comets in general, about how they age and evolve over multiple orbits? Is there a pattern here that applies to other comets, or is 3I Atlas an outlier, a comet with unusual properties that make its behavior exceptional? These are questions that can only be answered through sustained observation and comparative analysis. There is another layer to this story, one that touches on the nature of scientific discovery itself. When I say that astronomers call this situation paradoxical, I mean that it challenges the simple mental models we use to make sense of the universe. We like to think of celestial mechanics as predictable, governed by Newton's laws and Einstein's corrections, a clockwork cosmos where positions and brightnesses can be calculated centuries in advance. And, to a large extent, that is true. We can predict planetary positions with extraordinary precision, forecast eclipses millennia into the future, and send spacecraft on trajectories that thread the needle through gravitational keyholes millions of kilometers away. But comets, with their complex surfaces, heterogeneous interiors, and volatile-driven activity, remind us that the universe is not entirely deterministic, at least not in the ways we can currently model. There is an element of chaos here, sensitive dependence on initial conditions and small perturbations that can lead to wildly different outcomes. A crack forming in the wrong place, a pocket of gas venting at the wrong angle, a shift in surface albedo driven by a dust storm we cannot see. Any of these could alter a comet's brightness in ways that no amount of computational power can predict without knowing every detail of the nucleus's structure, and we simply do not have that level of information. This is not a failure of science. It is a reminder of science's limitations and its ongoing evolution. Every anomaly, every paradox is an invitation to refine our models, to ask deeper questions, and to develop better tools. As 3I Atlas continues its approach, astronomers around the world are coordinating observations, pooling data from professional observatories and dedicated amateur astronomers alike. This is a truly global effort because comets do not respect international boundaries or time zones. A comet visible from one hemisphere might be below the horizon from another, so continuous coverage requires a network of observers spanning multiple continents. The data from these observations will be compiled, analyzed, and eventually published in peer-reviewed journals, contributing to the long-term archive of cometary science. But in the near term, in the days and weeks ahead, we are likely to see updates, perhaps even dramatic ones. Will 3I Atlas continue to dim, fading into obscurity as it recedes from the sun? Will it plateau, maintaining a steady brightness as it coasts through the inner solar system? Or will it surprise us yet again, flaring back to life in a sudden outburst that sends its magnitude plummeting back down, making it brighter than before? All of these outcomes are possible, and that uncertainty is part of what makes this so compelling. Let me bring this back to the human element, because while we are talking about a comet millions of kilometers away, a frozen relic from the dawn of time, there is something deeply relatable about the mystery of 3I Atlas. It is a reminder that even in an age of advanced technology, even with telescopes in space and sophisticated computer models, the universe still has the capacity to surprise us, to do things we did not anticipate. There is a humility in that, an acknowledgement that for all our knowledge, we are still learning, still exploring, still occasionally baffled by what we find. And that is okay. That is, in fact, what makes science exciting. If we knew everything, if every observation confirmed our expectations, there would be no discoveries, no breakthroughs, no moments of genuine wonder. 3I Atlas, with its paradoxical dimming, is giving us one of those moments, and whether you are a professional astronomer or someone who simply looks up at the night sky with curiosity, you are part of this story. If you found this deep dive valuable, if it gave you a new appreciation for the complexities of cometary science, or just sparked your curiosity about what else is out there, do me a favor and hit that like button. It genuinely helps the algorithm push this kind of content to more people. And in a media landscape often dominated by sensationalism, every bit of support for thoughtful, detailed science coverage makes a difference. So, where does this leave us? Comet 3I Atlas is out there right now, a frozen wanderer the size of a city, moving through the darkness of space on a trajectory that will bring it closer to Earth over the coming days. And yet, it is fading from view, its light dimming in a way that defies simple explanation. The most likely cause is the comet's increasing distance from the Sun, the primary source of energy that drives its activity and makes it visible. But layered on top of that are fluctuations in surface albedo, internal changes within the nucleus, and instabilities in the production and distribution of dust. These factors interact in complex, non-linear ways, creating a system that is sensitive to small perturbations and difficult to predict. The observations coming in from telescopes around the world are giving us snapshots of this evolving system, but snapshots are all they are. We are seeing the comet at discrete moments, and the gaps between those moments are filled with processes we can only infer. Could there be a major outburst happening right now, at this very moment, that we have not yet detected because the light has not reached us? Could the nucleus be fracturing, pieces calving off like icebergs from a glacier, altering the comet's structure in ways that will only become apparent in the next set of images? These are not idle questions. They are the kinds of uncertainties that drive observational campaigns and motivate researchers to request more telescope time, to refine their instruments, to push the boundaries of what we can see and measure. The story of 3I Atlas is also a story about the nature of knowledge in astronomy. Unlike laboratory sciences, where experiments can be repeated under controlled conditions, astronomy is an observational discipline. We cannot manipulate the objects we study, cannot run controlled trials, or rewind time to see what happens if we change a variable. We can only watch, measure, and interpret, building models that fit the data and making predictions that can be tested against future observations. When those predictions fail, as they have with 3I Atlas's unexpected dimming, we are forced to revise our models to consider possibilities we had not previously entertained. This is the scientific method in action, not as a smooth, linear progression toward truth, but as a messy, iterative process of hypothesis, observation, revision, and refinement. It is through this process that our understanding deepens, not in spite of anomalies and surprises, but because of them. 3I Atlas is teaching us something, even if we do not yet know exactly what that lesson is. It is showing us that comets are more variable, more dynamic, more complex than our current models fully capture, and that realization, that recognition of the limits of our knowledge, is itself a form of progress. As we close, I want to leave you with a final thought, a question that lingers in the air like the tail of a comet stretching across the sky. What else is out there moving through the solar system that we have not yet noticed or fully understood? How many other objects are performing their own quiet paradoxes, dimming when they should brighten, accelerating when they should slow, defying the neat categories and predictions we have constructed? The universe is vast, and our surveillance of it, even with all our telescopes and detectors, is still incomplete, still biased toward the brightest, the nearest, the most predictable. 3I Atlas was noticed because it is relatively close and relatively active. But there could be dozens, hundreds, perhaps thousands of similar objects farther out, too faint to detect with current instruments, evolving and changing in ways we can only imagine. The dimming of this one comet, this one frozen fragment of the early solar system, is a window into processes that are playing out across the cosmos, and it is a reminder that the sky above us is not a static backdrop, but a dynamic arena where countless dramas are unfolding, most of them unseen, most of them still waiting to be discovered. The mystery of 3I Atlas is far from solved, and the answers, when they come, will almost certainly raise new questions, deeper and more intriguing than the ones we started with. And that, more than anything, is what makes this work worth doing.